Good to go? Great.
Yep.
Brian, finally, thanks so much for showing up. A little bit of a computer glitch as always. That's just how it is these days. It's a great pleasure to introduce to you Matt Colbrook. He's sort of local born in Cambridge, but is now at École Normale Supérieure. And he will be talking about, can stable and accurate neural networks always be computed? So please, Matt, the floor is yours.
Great, thank you, and thank you for the opportunity to talk. So this talk will be based on joint work with Vegard Anton, who's at the University of Oslo, and Anders Hansen, who just introduced me, at the University of Cambridge. So it's based on our paper of the same title, which you can find on arXiv, and then also hot off the press this morning on the arXiv, there's also a follow-up paper which extends these types of ideas to more general problems such as matrix completion. You can also find code here. So I will put these slides up on my website afterwards, so don't worry about keeping track of links and things like that if you're interested. Okay, so can stable and accurate neural networks always be computed? So we're all familiar with the interest in deep learning. So I've got here a fun graph just to show this to start off. So this plots the number of arXiv papers in machine learning per year. So you can see the exponential growth. So to put this in perspective, if you set yourself the foolish task during lockdown of trying to read every single one of these papers, you'd have to read continually and read a paper every 4 minutes, night and day. So it's incredible. Yeah, I don't recommend you do that. It's impossible.
Thank you.
Okay, so it's really fascinating to see this growth, and also represents a great opportunity for us as mathematicians. Okay, so AI is all over the place now, so there's lots of different applications. For example, AI techniques are now replacing humans in problem solving. So self-driving cars is probably the most famous example, but you also have things like mathematical proofs. So Facebook now has a system that can perform symbolic manipulations for proofs and also integral equations and things like that. You also have potentially more worrying applications such as automated weapons systems, but also ones that are closer to home to the topic of this talk, such as diagnosis in medicine. Okay, so AI is replacing humans in problem solving, but it's also replacing established algorithms in the sciences. So the one most relevant to this talk is medical imaging, for example, MRI, but you also have things like solving PDEs, which we've seen in previous talks in this series as well. Okay, so let's get to the point. So will AI replace standard algorithms in medical imaging? Okay, so this is predominantly the type of problem that I'm interested in this talk. And I'm going to start off with a paper that appeared in Nature a couple of years ago, which proposed a neural network trained end-to-end for MRI reconstruction. And it concluded that this method provides superior immunity to noise and a reduction in reconstruction artifacts compared with conventional handcrafted reconstruction methods. Okay, so on the face of it, this looks like fantastic news. There's lots of opportunities for applying this type of method in lots of different problems. But we're going to see a bit later on that you have to be a bit careful before declaring sentences like this. In particular, this neural network happens to be unstable. And I'll give some numerical examples towards the end. Okay, so there's very strong confidence and optimism surrounding deep learning. And this is captured by this quote of Geoffrey Hinton, who recently won the Turing Award, who said that they should stop training radiologists now. Okay, so this is quite interesting. I'm not sure I'd trust a neural network quite yet. And the reason for this is that there's also something called AI-generated hallucinations. Okay, so these have been discovered recently in lots of different contexts. So I've got here a snapshot from a BBC News article, which captures it nicely by saying that For example, computers can see a sea turtle as a gun or hear a concerto as someone's voice. So, for example, in diagnosis, medical diagnosis, it could be that the machine is thinking there's a tumor when there isn't, or vice versa. And this is potentially very dangerous in high-stakes scenarios. For example, this is a sad story of someone who got killed by a self-driving car because the car had been trained to ignore things like plastic bags going across the road. So those would be false positives. So it'd been trained to ignore those to the degree that it also produced false negatives. Okay, so the person crossing the road was not detected by the algorithm, and then the car hit them and killed them, sadly. So you do have to be very careful when deploying these techniques. Probably a more familiar example is deep fool. So this is a different problem. This is image classification. Okay, so you adversarially perturb the image slightly, and that causes a change in the classification. So these perturbations aren't detectable by eye. So for example, this dog suddenly becomes an Indian elephant, and then you've got lots of different examples here. You can also do cool stuff like universal perturbations across images and across even neural networks as well. So there's really an arms race on the one hand between people who are creating these adversarial type attacks and people who are defending against them as well. Okay, so that's image classification for this problem. But you also have a similar type of phenomenon in inverse problems. Okay, so this is a paper that was written by two of my collaborators, so Vegard and Anders and some others, which looked at similar adversarial type perturbations for image reconstruction. Okay, so they took a whole bunch of neural networks that showed that if you perturb the input slightly, you get a very different image as the output. So let's look at an example of this. So this is a network for MRI reconstruction with 33% subsampling. So you can find the network here. I won't go through the architecture or anything. And on the left-hand side, I have the image. And what I'm going to do is I'm going to add small perturbations to the image. Okay, so the whole point is that the left-hand side won't change very much, or it will be very hard to see the change. The right-hand side will show the reconstruction of the neural network. Okay, so let's go for the first perturbation. So I'll go backwards and forward a couple of times so you can try and spot the difference on the left-hand side. It's very difficult. But you see a huge difference on the right-hand side. For example, these artifacts here that I've labeled with these arrows. Okay, so let's now increase the perturbation size. Okay, so again, hard to see the difference on the left-hand side, but the right-hand side, there's a huge difference. And again, stronger perturbation leads to a stronger perturbation of the output. So actually, potentially the most dangerous ones, one of these perturbations is the first one, because if you showed, say, this image here on the right-hand side, the doctor, they'd obviously see that something had gone wrong in the reconstruction. But this one's much more subtle with these perturbations here. Okay, so that's adversarial type perturbations, where you try and train or algorithmically find for a given neural network a perturbation that wrecks your output. You can also do the same thing with random perturbation. Oh, before I show that, this is just a state-of-the-art reconstruction with shearlets and TV to show that I haven't cheated, right? So here's the image, here's the reconstruction. So it is possible to get stable and accurate reconstruction for this particular problem. Okay, so random perturbations. So here what I've done is I've added Gaussian noise and then looked at the worst reconstruction over a particular sample size. So this is worst over 100. So you can see again, you get this artifact here. So I'm not a doctor, but it seems to me that this vessel type thing closing is probably bad. So this is worst out of 100, worst out of 20, and worst out of even 1. So these perturbations can occur in practice as well, randomly. Okay, and then in clinical practice, you also see them popping up in the FAST MRI challenge. So Facebook and NYU run a competition, which is similar to the ImageNet classification, but now for MRI reconstruction. Okay, so different groups all over the world will submit methods that have been trained on a data set that they're given, and then they're tested on unseen data. So here you see these types of hallucinations appearing. So for example, the neural network adds what looks like some sort of vessel or something in the brain here, similar effect here, and also here. So this just shows the differences. Okay, so you can see these artifacts here. And this is very worrying. So the most recent version of the Fast MRI challenge actually had one of the tracks was to try and get rid of these AI hallucinations. Okay, so that's all a bit doom and gloom, but there's still something there, right? That neural networks can hopefully still be used, but I think there needs to be a bit of caution, and this also echoes a familiar story for many mathematicians. So I'm going to go back 100 years to the start of the 20th century, to David Hilbert on the right-hand side here. So Hilbert was a fantastic mathematician, and he had a grand vision to provide a secure foundations for the whole of mathematics. Okay, so you can't get more ambitious than that, really. But he believed that mathematics should be written in a precise language, manipulated according to well-defined rules. And there were three parts of this program. So completeness, this just means a proof that all true mathematical statements can be proved within your formalism. Okay. Consistency, this is a proof that you can't ever obtain a contradiction. And perhaps most interesting for us is decidability. So an algorithm for deciding the truth or falsity of any mathematical statement. And Hilbert presented a list of problems to the International Congress of Mathematicians. So this is a very famous list. You can find it by just Googling. And his 10th problem on that list really reflects this well, and also note how it's phrased. So he asks, provide an algorithm which for any given polynomial equation with integer coefficients decides whether there is an integer valued solution. Okay, so Hilbert says, provide an algorithm, not whether does there exist an algorithm. Okay, so Hilbert strongly believed that such an algorithm must exist, but of course he was no fool, and realized that there hadn't been a proof of these three key things. Okay, so he set forth this grand program, and then along came Gödel on the left here and Turing, who were the ultimate party poopers of the 20th century, and showed that Hilbert's optimism could not be realized. Okay, so Gödel showed that there exist true statements in mathematics that cannot be proven, and Turing showed that there exist problems that cannot be computed by an algorithm. Okay, so far from sort of stopping this program and mathematics dead in its tracks, these results actually led to a lot of flourishing of different areas. For example, Gödel is widely looked on as the father of modern logic, and then Turing as the father of modern computer science. So understanding the foundation, so understanding what is and what is not possible within a certain area of mathematics, not only gives you better understanding, but allows you to figure out which directions or which techniques that you can use for different problems. And often you discover new methods in the process. So Hilbert's 10th problem, by the way, it was shown in 1970 that there exists no such algorithm. Okay, so the phrasing here is actually incorrect. Okay, so that's sort of a history lesson, but I'd like to say that a similar type of program for the foundations of deep learning and AI is currently needed, because at the moment we're still stumbling in the dark somewhat, trying to figure out what we can and cannot do. So interestingly, Steve Smale, another very famous mathematician, was asked to provide a list of mathematical problems for the 21st century in a similar fashion to Hilbert for the 20th century. And his 18th problem was, what are the limits of artificial intelligence. Okay, so this was 20 years ago. So already, I think Steve Smale was ahead of his time here. And what would a program of foundations in this area look like? Well, there are two types of results. Boundaries of methodologies. So you come along and you say, okay, I have this amazing method. What can I do with it? What can't I do with it? So you try and figure out, how far can I take the method? And then you also have universal or intrinsic boundaries. So these are results of the form, no algorithm can solve this problem with this given information. And we'll see an example of a result of this form later on in the talk. There's also a key difference between existence and construction here. So again, this echoes Gödel's result here. There are there exist true statements in mathematics that cannot be proven. So similarly, when we apply say neural networks to a particular problem, we often have existence results of our things like the universal approximation theorem. But these aren't enough, because you actually want an algorithm or a way of training the neural network to solve your problem. And we'll see this important difference as well when I present a boundary result. Okay, so when you're doing this, you also need to incorporate two pillars of numerical analysis: stability. Okay, we saw how that broke with a particular neural network earlier on, and also accuracy. Okay, so there's no point having a very stable neural network if it's not very accurate for your problem. Okay, so the goal for the rest of this talk is to develop some results in this sort of direction, okay, for inverse problems. So without further ado, let me describe the mathematical setup. So I have a matrix A that describes my modality. For example, it could be a discrete Fourier transform if I was modeling MRI. And I'm given access to a collection of measurements y equal to ax plus some noise, and x is the guy that I want to recover. Okay, and I'm going to split up the rest of the talk into sort of three subsections. I'm going to first present a fundamental barrier, okay, and a possibility result. Then I'm going to look at sufficient conditions for overcoming this barrier and introduce fast iterative restarted networks. Okay, so it's a positive result. And then I'm going to look at these networks in the context of balancing stability and accuracy with some numerical examples at the end, and end with some sort of open problems for future work. Okay, so I'm going to take my inverse problem and I'm going to look at these three optimization problems. Okay, so these are standard benchmark problems. There's L1 minimization to subject to a constraint here. So this is known as basis of soup. Lasso, which probably needs no introduction for the audience. And then something called square root lasso, which differs by getting rid of this square term here. Don't worry too much about the precise details of these three methods. The important thing is that these are three standard benchmark problems. They're all convex, they're all nicely behaved, etc. So I'm going to denote the minimizing vectors, okay, by xi for each of these problems. Okay, so the vectors that solve these optimization problems. And you might wonder, why have I suddenly gone from this inverse problem to these three optimization problems? And it's just to avoid sort of bizarre and pathological mappings that can occur. So these problems are well understood, they're well behaved, and they're well used. And actually, it turns out that the solution maps here are, in some sense, simpler than the sort of ill-defined solution map here. Okay, so this gives me a stronger impossibility result. Deep learning has actually now been used to speed up the solution of optimization problems such as these as well. Okay, so the setup, and this is potentially a horrible slide, so I'm going to sort of try and describe what it means in words as I go along. So I need all of this to be completely precise in the theorem that follows. So I'm given a modality A, and I'm given a collection of samples, yk, so finite collection, But in practice, of course, when I'm given this information, I can never store or measure it to infinite precision. So what I'm going to assume is that my algorithm can access this information to any accuracy that it wants, to any precision. So this means that I can access any AN, which is arbitrarily accurate for the matrix A, and any YKN, which is arbitrarily close to the sample YK. And I'm also going to throw in some extra information that just helps the algorithm as much as possible, which is that I assume that I can solve these the perturbed optimization problems with these inputs here to any accuracy that I want as well. Okay, so this is just basically saying that I'm giving the algorithm as much information as it could possibly want to be able to solve these problems. Okay, so the training set associated with my modality and my samples is just all of this information. Okay, so in a nutshell, what I'm doing is I'm allowing access to arbitrary precision training data. Okay, so the question is, given a collection omega of such A and samples S, does there exist a neural network that approximates my solution map of the PJ? And if so, can it be trained by an algorithm? All right, so what can possibly go wrong when we try and do this? So recall that we want to solve these three optimization problems. First of all, there might not exist a neural network that can approximate the solution map. Thankfully, you can prove by the universal approximation theorem that does not hold. And actually, you can prove that not only do you get the solution map, but you also get a stable neural network as well. So you get a stable and accurate neural network. So there does exist a good neural network for this problem. What else could go wrong? There might exist a neural network, but we might not be able to construct or train it by an algorithm. Furthermore, even if there exists an algorithm that trains the neural network, it might need prohibitively many samples. So we'll see that both of these scenarios can actually happen, even though there exists a good neural network for the problem. Okay, so here's the theorem, and this is the longest theorem in the talk. So don't worry if it seems like a very meaty slide. I'll go through it slowly. So I'm going to take any of my problems PJ, any dimension n, at least 2. So remember, n is the dimension of the vector that I want to recover. Any m less than n, so m is the dimension of the samples that I see. And I'm going to take any positive integer k greater than 2, any positive integer l. Okay, then given these, there exists a well-conditioned class omega of elements A and S. So remember, A is the modality, S are the samples, such that the following hold. So before I go through these 3 points, I should say that well-conditioned here is in terms of standard condition numbers in the literature. So all of those condition numbers are bounded by 1. So this is a well-behaved class. The result is nothing to do with scaling or discontinuity or anything like that. But for this class, which typically depends on K and L, the following holds at the same time. There does not exist any algorithm that, given your training set, produces a neural network so that the minimum error over your sample is bounded by 10 to the minus K. So in other words, you can't get K digits of accuracy. Furthermore, you can't do this in a probabilistic sense, with probability greater than 1/2. Okay, so even if I allow random things like stochastic gradient descent, etc., I can't solve this problem to K digits of accuracy. However, at the same time, there does exist an algorithm that produces a neural network so that the maximum error over my samples is bounded by 10 to the minus K minus 1. So in other words, I can get K minus 1 digits uniformly across my whole across the whole problem that I'm interested in. Okay, so that's good, but at the same time, if I have such an algorithm for any integer m and any probability p in this interval, there exists a training set. So you can think of this as an adversarial training set so that the probability of either not achieving k-1 digits or needing a training data size greater than m is greater than p. Okay, so these are two negative results, which reflect these two problems here. So, okay, there doesn't exist an algorithm. There does exist an algorithm, but it becomes prohibitively expensive. But at the same time, you can show that there does exist an algorithm that produces the neural network, which is correct to k-2 digits and only requires L training data. Okay, so in words, there are nice classes omega, so they're well conditioned, where one can prove neural networks with great approximation qualities exist. So they're stable and they're accurate. But no algorithm, even randomized, can train such a neural network to k digits with probability greater than half. You can get k-1 digits, but the algorithm needs arbitrarily many training data. And then you can get k-2 digits with only L training samples. And this result is independent of neural network architecture. Okay, so it's a universal barrier. It's independent of whatever architecture you choose. So this is really showing you that there's a difference between existence and computation, right? So if I go back here, we know that this problem here can't happen because of the universal approximation theorem. Okay, however, these two problems can happen. Okay, so universal approximation theorems are not enough for applying these methods in practice. And then again, so the conclusion, theorems on existence of neural networks may have little to do with the neural networks that you actually produce in practice. Okay, so let's see an example of this actually happening for a real world example. So what I've got here is an example where I've taken A to be a discrete cosine transform and subsampled dimension 19, full dimension 20. So it's a nice problem. I've looked at the sample size of 8,000 and I've looked at solutions that are 6 sparse. Okay, so I won't go through the details of the experiment, but the point is that this is a very nice problem that you expect to be able to solve easily. So what I've got here in these two columns are the reconstruction from Lister. So Lister is a learned version of ISTA. Okay, so the very famous algorithm. And then the second column is the reconstruction error for FireNets, which are the neural networks that I'll introduce later on in the talk. And what I've got here is the increasing precision. Remember, we had arbitrary precision allowed in our algorithm for different classes corresponding to the different k in the theorem. So remember, 10 to the minus k is the barrier that I can't get beyond. Okay, so these first three are for 10 to the minus 1. So you can see that even as I increase the precision, I can't break this barrier. Similarly for 10 to the minus 3, okay, so I can't break 10 to the minus 3 and then 10 to the minus 6 and so on. Okay, so this also occurs in practice. Okay, so that's all doom and gloom. I won't go through the construction of those classes because it's a bit complicated, but what I will say is that part of it is due to a subtle difference between the objective function and the minimizers when you solve optimization problems. Okay, so we're all used to the idea that you can somehow solve convex optimization problems, and what we mean by that is that you can produce an x which is arbitrarily close, which produces an objective function which is arbitrarily close to the minimum. But it turns out that this doesn't in general imply that you are arbitrarily close to the solution vectors. So what we need are good input classes or good model classes where a small suboptimality in the objective function leads to being close to the set of minimizers. And we'll see later that that you can produce natural conditions which give you this type of result for image reconstruction. Okay, so I'm going to look at something called sparsity and levels. So don't worry too much about trying to read this definition. The main thing is this picture here. So suppose I have a vector rather than looking at just sparsity, I'm going to look at sparsity and levels. So I'm going to split it up into different levels, and then each one of these will have a different sparsity coefficient. So in these examples for images, a natural thing to do is to look at wavelet levels. Okay, so I'm going to denote the set of SM sparse vectors. S just decodes the sparsity parameters. M is just encoding the levels. So I'm going to denote the set of all SM sparse vectors by sigma SM. And then I'm also going to look at the distance of a vector X to sigma SM measured in a weighted L1 norm. Don't worry about the weight. You can just view this as the usual L1 norm. Okay, so there's this quantity here. So that's telling you how close a vector is to being sparse in levels. And we'll see that this appears in our error bounds later on. Okay. And then final definition, I need something called the robust null space property, which is hopefully familiar to those of you who know a bit about compressed sensing. So the idea is that if I have a matrix A, then it satisfies the bit of a mouthful, but the weighted robust null space property in levels of order SM. So remember, this encodes the sparsity structure with these constants here. If for any SM support set, this inequality here holds. So let me just explain what this is saying. So if X is SM sparse, okay, I can take delta to be its support, and this term here vanishes. So that's telling me that I can control the size of X by the size of AX. And remember, A is subsampled. Okay, so this is why it's called, this is why null space appears in the name of the definition, right? Because you're controlling the size of X by the size of AX. So you can view this as some sort of perturbation term, right? And in fact, that this leads to a bound that involves this quantity here. Okay, so you can go away and you can produce the following L2 estimate. So if I take any vectors Z1 and Z2, I can bound their difference by something that's small. I'll explain what these terms are in a second, and then something that looks like an objective function difference. Okay, so this term here just tells you how close Z2 is to being sparse in levels. This term here, oops, is the noise. Okay, so if I go back to where is it? This here, that just corresponds to the measurement noise E. This term here. So I expect this first thing to be small, and then I have something that I've written out like this, which is just the difference in the objective function here between Z1 and Z2 of the square root lasso. Okay, so L1 plus AZ minus Y. Remember, Y are the measurements that I see. Okay, so this is precisely something that looks a bit like this. And it turns out that you can use this to construct accurate and stable neural networks as follows. So we provide an algorithm that does the following. You provide it with sparsity parameters and weights. So often you'll know sort of suitable selections of these by looking at things like phantom images and stuff like that. So you don't have to worry too much about those. You also feed it the matrix A, again with the, remember we had the arbitrary precision approximations to A. Satisfying the robust null space property in levels with these constants here. And then you need these three inputs here. So these are the most important things to remember from this first line. So delta, B1 and B2. Okay, so you feed the algorithm that information. It goes away and it spits out a neural network phi n with order n layers and width bounded by capital N. Okay, so I'm not cheating by taking a very wide neural network. With the following property. If I have X, so the thing I want to recover, and Y, the samples that I see, such that these three conditions hold, and then I get good recovery. So let me just explain what these three conditions are. So the first is saying that the the distance of x to sparse and level vectors plus the noise of the measurements is bounded of order delta. Okay, so this describes sort of the model class of x and y that I'm interested in. X is is bounded of order b1, so I'm just working on a ball, and similarly y is bounded of order b2. So this just allows me to work on a compact set. Then I have the following stable and exponential convergence guarantee in n. So phi n of y, the difference of that and x is bounded by delta, the noise term, and you can show that you can't actually beat the noise term in general, plus something that decays exponentially in the number of layers. So what you expect to see, if you plotted the arrow in terms of the number of layers, exponential convergence till you hit the plateau of noise. And I'll show you a graph of that in a second. Okay, so a few more detailed comments. I won't go through the reconstruction fully, but the architecture is inspired by restarted and reweighted unrolling of primal dual algorithms. And as well as stability, the robust null space property actually gives you the exponential convergence. For example, if you just try to naively unroll iterative methods, you typically get very slow convergence of the order delta plus something that decays like 1 over n. Okay, so it's very slow. But here we've got exponential convergence. If we don't know the constants for the robust null space property levels, okay, so that's these constants appearing in this inequality here, you can perform a log grid scale search for them, and this only increases the width by a factor of log n. So you don't really need to know them. And the results that we prove actually also bounds the error when you only approximately apply the neural networks. So you get numerical stability as well. But I've swept that under the rug in stating the theorem. Okay, so if you're interested in sort of a broader framework of this type of method in other contexts, then you can look at this this paper here that I mentioned at the start. Okay, so I'm now going to look at an example on image recovery. So I'm going to go through this theorem very fast and not dwell on it. So here my my A corresponds to either Fourier sampling or binary or Welsh sampling. And the point is that you can design a random sampling pattern so that A satisfies the robust null space property with certain parameters here. And then you can wrap the previous result in a reconstruction result of the following form. So pick any delta, and then let J be the set of all Y equal to AX plus E, where X is bounded of order 1, and the maximum of the distance of X to sparse in level vectors, and the noise is bounded by delta. Then there exists an algorithm that constructs a neural network, okay, with only log of delta to the -1 hidden layers. Okay, so it's logarithmic in the accuracy that you want, so that with high probability you obtain the following reconstruction. Okay, so you get reconstruction to accuracy delta for all measurements in your chosen class that satisfy these inequalities here. Okay, so you can apply it in things like MRI. Is the point that I'm making, and you only need logarithmic number of layers, logarithmic of the accuracy that you want. Okay, so let's look at this for a particular example. So here I've got an image of a cup and an apple, but I chose this image because there's some nice details in the background. So this is the image. This is the zoomed in section here corresponding to the red square. Here I've got the reconstruction using my neural networks for Fourier sampling, okay, and here for binary sampling. So these were for 15% subsampling, and then I added some, I think it was 2% Gaussian noise to the measurements. So it's accurate, but let's also look at the accuracy in terms of the number of layers. So remember, we expect a plateau down to the noise level, and this is exactly what we're seeing here. So the blue curve shows the reconstruction of the image. So the error of the reconstruction of the image. So it's a relative error, and you can see you get exponential convergence down to this plateau. And then the red curve shows the suboptimality of the objective function. So I didn't say it, but if I go back to this theorem here, the objective function also satisfies a bound like this for suboptimality. So this behavior is completely expected. So this is for Fourier, and then this is for binary sampling. So this is the number of hidden layers. So you see the theorem holding in practice. Okay, now let's look at stability. So this is the automap network that I mentioned near the start. So that was the paper that appeared in Nature. This image is taken from the paper of Vegard and Anders that I mentioned earlier as well. So here I've got an image of a brain, and then I'm going to perturb the image slightly in the top row with adversarial type perturbations, and then you can see that the reconstruction becomes very bad, right? So it's very unstable. So small perturbations lead to of the input lead to large perturbations of the outputs. So now let's do the same thing for fire nets. So those are the neural networks appearing in the theorem that I showed you a couple of slides ago. And I should say before I show you the result that I'm going to compute new perturbations, new adversarial perturbations for the new neural network. Okay, so I'm trying to break fire nets as opposed to using the same perturbations here. Okay, so this shows the perturbations. These were all chosen to be at least as large as the perturbations in the previous slide. And then you can see the reconstruction is completely stable. And if you actually plot the reconstruction error against the perturbation size, they are proportional, which is exactly what you expect from this theorem here. So that's this delta term appearing. Okay, so that's excellent. They're stable and they're also accurate. Curiously, you can also use these to stabilize unstable neural networks. So here, what I've done is I've taken I've taken automap, so the unstable network, and I've taken its output as an input to FireNet. So I've concatenated the two neural networks, and this is what you get. So this is the adversarial perturbation for automap. This is the output of automap, which you feed into FireNet, and you get a good reconstruction. And you can also do the stability test for the fully concatenated neural network, and you get stability as well. Okay, so that's good and interesting. So we haven't really explored how you could use this. So, for example, you could imagine you'd have a very accurate neural network, which is unstable on certain images, but it might be unstable on a small subset of images. And then you could think of adding a FireNet or something similar to that neural network to stabilize it, but you also get the good accuracy on the other images as well. Okay, so stability and accuracy. I'm going to end with this numerical experiment. So hopefully it's obvious to anyone with a background in inverse problems that you can't get unlimited stability as well as unlimited accuracy. Okay, there are fundamental barriers preventing you from doing this, right? Because the problem is ill-posed. So what I'm going to do is I'm going to take a collection of random ellipses as my training data. I'm going to look at a zoomed in section here in this red box in the middle column. Okay, and I'm going to apply an adversarial type perturbation, which you'll see the effects of in this middle column here. And I'm also going to be interested in recovering detail in the form of text. Can you see it? So that corresponds to this blue box here. Okay, so we've got stability in the middle column, accuracy in the right column. So the first neural network I'm going to test is simply a UNet trained without noise. Okay, so this is the original plus worst case noise of the adversarial perturbation. So you can see it's very small perturbation. And then this is the reconstruction, and you can see there are severe artifacts, so it's unstable. But it's very accurate. So you see this this text here can be read. So now I'm going to do a similar thing where I take a UNet, but now I'm going to train it on noisy training data. So I'm going to jitter the training data, and this is what I get. So I get a completely stable reconstruction in the middle, but the detail gets washed out. Okay, so in other words, I'm stable, but I'm not accurate. So I've somehow jumped between the two. So now let's look at FireNet. So FireNet is very accurate. You can read the text. It's also stable, not as stable as this network here. It's still a lot more stable than this network here. Okay, so somehow I'm sort of balancing between the stability and accuracy, and sort of figuring out where I am on this trade-off curve is a very hard problem that is predominantly open at the moment. So that's one of the things that I want to conclude with in the next slide. Okay, so to summarize, there's a need for foundations in AI and deep learning. So our particular results show the following. There are well-conditioned problems where mappings from the training data to suitable neural networks exist. So by that I mean stable and accurate neural networks. But no training algorithm, even randomized, can approximate such a neural network. The existence of algorithms for getting your desire, for obtaining your network, depends on the desired accuracy. Okay, so we showed that for any integer k, at least 3, there exist well-conditioned problems where simultaneously you have the following. Algorithms may compute neural networks to k-1 digits, but not k. Achieving k-1 digits requires arbitrarily many training data, but you can achieve k-2 correct digits with only one training data. Okay, under specific conditions, there are algorithms that compute stable and accurate neural networks. So I gave you an example for fast iterative restarted networks. So these converge exponentially in the number of hidden layers until you hit that, plateau, which you can prove is an intrinsic bound. Okay, and I also proved that FireNets withstand adversarial attacks. We saw that in practice. And then finally, there's a trade-off between stability and accuracy in deep learning. So how do we optimally traverse this stability and accuracy? FireNets showed that that had some sort of balance between the two, but of course aren't the end of the story. And I think these questions, well, I hope they inspire you. They at least inspired me to take up the challenge of mathematics in deep learning. Okay, that's all I had to say. Thanks for listening.
Hi, Matt. Thanks for
Hi.
this talk.
Thank you.
I have one question to your initial results with the accuracy and the training. So my question is basically, how much is this more like a result in general on numerical accuracy? Because obviously you want to approximate something to, like up to a certain digit of accuracy, which, I mean, in general is something, I mean, since you only, I think you made the point that when you work with basic approximations, which you always have so fixed point, not fixed point, sorry, when you have, well, when you can basically not represent real numbers, but you actually just have a certain degree of accuracy. So actually the phenomena you describe, are these actually more general and dependent on sort of numerical analysis and the fact that we have to work with approximate results rather than specific, intrinsically like problems that arise with neural networks, or is it actually they are intrinsic to neural networks?
Excellent question.
And other numerical algorithms don't have the same issue. It looked a bit like it might be the former, and that would be, yeah, sort of my question. Hope that was clear.
Yeah, that's a fantastic question. So let me just go back. So yes, it does hold, regardless of the method that you use to reconstruct the vector. So whether that's a neural network or another algorithm, like splines or whatever. So you're absolutely right that the key thing that causes this is this arbitrary precision. So the reason I've stated it in terms of neural networks is that you get the curious result where you can prove there exists a good, stable, and accurate neural network. But you're right. So it does hold for other reconstruction techniques. So it's really a numerical analysis type phenomenon as well, which is why I think results like this are sort of our bread and butter. Right, we have lots that we can bring to the table for looking at deep learning and AI. Hopefully that answers your question.
Absolutely, I think because I agree, because I think it's we often obviously brush it under the carpet that we work with finite precision and not like infinite precision.
Yeah.
No, thank you.
Right. Other questions? Oh, yeah, please go ahead. We have 30 more minutes to talk.
I have a follow-up question. In terms, because you talked much about the training error and obviously the ramifications for training. Can you say something about the validation error? Because obviously when you specifically talk about neural networks, what people often care is how a neural network performs on unseen samples. And obviously we have seen from your numerical results that you can do can get obviously stable results. But in terms of the results that you provided and the limitations, is there something carry over to validation error?
Yeah. So this impossibility result is for a collection of finite samples, right? So you can view it as an impossibility result even on your training error. So you can do a similar thing for validation, but then of course you'd have to be very careful about what are the type of vectors that you want to recover and things like that. So that's kind of similar to what we've done actually in practice here. In terms of the positive result, so this result here, what this is telling you is that you've got good accuracy over a whole model class of vectors that are approximately SM sparse. So you get good generalization error if you looked at different images. And I sadly I don't have the pictures here to show, but if you go to the paper in the appendix, there's like a whole lot of different images that we show. You get a similar phenomenon. Okay. Hopefully that sort of answers in part.
Right. Other questions? Well, then I think we should thank Matt again. Thank you, Matt. Okay. Then I think there's coffee in the hall. Thank you.
Thank you.